This call is now being recorded.
So next we will focus on singular value decomposition. Okay, so this term you might be first hearing this term, singular value decomposition, or SVD. So you might not have studied this SVD in your mathematics class. Okay, so this SVD or singular value decomposition is a linear transformation. Okay, it's a linear singular value. SVD stands for singular value decomposition. So just like your eigenvalue decomposition, this is also linear. This is also a linear transformation. So what do you mean by transformation? Transformation is basically transforming a matrix or mapping a matrix in another space. Okay, transforming or mapping of a matrix into another, or a vector into another space. So for what purpose we are doing this transformation? So transformation of vectors, we are mainly doing transformation of vectors for the purpose of scaling as well as for rotating. So actually transformation means it's a combination of rotation and transformation. That means we are mapping to a new space. They are mainly, this SVD is mainly used for the purpose of the dimensionality reduction, that we will come to that later. Okay, so first of all, please understand that SVD is a linear transformation. That means it maps a particular vector into another space for the purpose of that. Actually it is doing rotation as well as scaling. It has got many image processing applications also, this SVD. So like this is also just like your eigenvalue decomposition. Eigenvalue decomposition you have seen in the previous class, isn't it? So like eigenvalue decomposition, this is also a decomposition of a matrix. Okay, so but here the difference between eigenvalue decomposition and SVD is that eigenvalue decomposition is for square matrix only. What do you mean by square matrix? Square matrix means same number of rows and columns, the number of rows equal to the number of columns, isn't it? So eigenvalue decomposition is for a square matrix, whereas SVD allows you to decompose for a rectangular matrix. Rectangular matrix means it has different number of rows and columns. The number of rows and columns are not same. That is a rectangular matrix. So SVD allows to decompose a matrix into decompose a rectangular matrix, whereas eigen decomposition, it can be applied only for a square matrix. So that is the difference between eigen decomposition and SVD. Okay, now SVD decomposes the matrix into three different matrices. SVD decomposes the matrix into three different matrices, which are the three matrices. Suppose A is a matrix. A is a rectangular matrix. Okay, A is a matrix, and we can decompose A into three matrices like U, S, and V. Okay, here U, S, and V are the three different matrices. That means A can be decomposed into U, S, and V. We will see shortly what are U, what is U, what is S, and what is V. So in effect, we can write matrix A as U into S into V transpose, U into S into V transpose. So in short, we can write the matrix A as U into S into V transpose. Okay, where U and V, they are orthogonal matrices. Okay, they are orthogonal. U and V are orthogonal matrices. So what are the speciality of orthogonal matrices? Orthogonal matrices, yeah, you have U. Suppose U is an orthogonal matrix, U into U transpose, it will be equal to I. What is I? I is identity matrix. U transpose equal to U transpose into U equal to I. V is also an orthogonal matrix, so this satisfies the property V into V transpose is equal to V transpose into V, that is also equal to I, identity matrix. So orthogonal, U and V are orthogonal vectors. U and V are orthogonal vectors or orthogonal matrix. So U into U transpose is equal to U transpose into U equal to I, where I is a identity matrix. So this property holds only for this orthogonal matrices. U into U transpose is equal to U transpose into U equal to I. That property holds for orthogonal matrices. Okay. And what is S? S is a diagonal matrix. S is a diagonal matrix. What do you mean by diagonal matrix? It has only, the matrix has only elements in the diagonal elements. Okay. Diagonal. So only has elements in the diagonal. That is called diagonal matrix. Okay. We call S as a scaling matrix also. We call S as a scaling matrix. Okay, rotation as well as scaling. The transformation is containing rotation as well as scaling. So scaling means what? The increasing the length of a vector. What do you mean by scaling? Scaling means scaling to by a factor of 2, means increasing the length of a vector. It is not like rotation. Rotating means we are changing the axis of rotation. Here scaling means we are increasing the length of the vector. So this factor S is a factor which allows scaling. So it is called scaling matrix. S is a factor which allows scaling property. Okay, that is why it is called scaling matrix, or it is a diagonal matrix. We can see all the elements on a diagonal. All the other elements will be 0. Okay, we can see non-zero elements on the diagonal. All the other elements of the matrix will be 0. That is why it is called a diagonal matrix. Okay, now what is A? Here you can see that A is a matrix. We can decompose A as U, S and V transpose, isn't it? Okay, so what is A? What do you mean by A? A, this is a transformation matrix. Actually, we are doing some manipulation in the orthogonal vector V. Here we can see V. So V is an orthogonal vector. So you can transform this V by using a transformation matrix A. Actually, you are transforming V vector or V orthogonal vector by using the transformation matrix A, and ultimately you are getting U. Okay, so by some transformation on V, you are getting another orthogonal vector which is called U. Okay, so A is called the transformation matrix. Okay, A is called the transformation matrix. Okay, and the original orthogonal vector is V. Here V is the original orthogonal vector. Here V is the original orthogonal vector, and A is the transformation matrix, and the transformed vector is U. So the original orthogonal vector is V, A is the transformation matrix, and U is the transformed vector. Okay, so you are applying some transformation to V. Okay, by using A. Okay, and the resulting one is U. Okay, and you are scaling by using a factor of S. That is the idea. Once again, I repeat, you are transforming an orthogonal vector V by using a matrix A, where A is the transformation matrix, and ultimately resulting in U. U is another orthogonal vector with a scaling factor of S. So that is the idea. Okay, so this S is also called singular value matrix. S is also called, S is, as I have already told you, S is a diagonal matrix. Okay, this S is also called a singular value matrix, or it contains singular values of the matrix A. Okay. Now, we will later come into singular values and all. Don't worry about that. Okay. Now, transformation is actually a combination of rotation and scaling. So, as I've already told you, transformation means it's a combination of rotations and scalings. Okay. Now, we will continue this AV equal to US. This will hold because you are transforming a vector V, which is an orthogonal vector V, by using the transformation matrix A. So AV equal to the, what is the resultant one? Resultant one is U. U with a scaling factor S. So AV equal to US. What is AV? AV means you are transforming the orthogonal vector V by means of a transformation matrix A. And what is the resulting one is U. Okay, U is a scaled version. So you multiply by the factor S. Okay, so AV equal to US. Okay, that means ultimately you are doing rotation and scaling on the V vector, on the V vector. So that is SVD. SVD is actually doing this scaling and rotation. Okay, next AV into V inverse. So you just this equation, in this equation you post multiply by V inverse. You just multiply by V inverse, post multiplying by V inverse LHS and RHS. So what you will get, AV into V inverse is equal to US into V inverse. Okay, what is AV into V inverse? What is V into V inverse? V into V inverse always equal to I. I is the identity matrix, isn't it? So A, here V into V inverse is equal to I. What is I? I is the identity matrix. Okay, so this will reduce to A. A into I means A. Okay, A equal to US V inverse. US V inverse. So what is V inverse? V inverse is actually V transpose. Why? Because the transpose for V is an orthogonal matrix. V is an orthogonal matrix. So instead of V inverse, you can write V transpose, because for an orthogonal matrix, the transpose is same as the inverse. Once again, I repeat, for an orthogonal matrix, the transpose is same as the inverse. So you can just replace V inverse by V transpose, and you will get A is equal to U into S into V transpose. So that is how this SVD comes into picture. Okay, A is equal to U into S into V transpose. So ultimately you can decompose this A matrix as U, S and V transpose. So when you multiply U into S into V transpose, you will get back A matrix. Okay, so that is SA matrix is decomposed into three different matrices, U, S and V. So like you will get this equation, A is equal to U into S into V transpose. That is very important. Now, how to find the V values? So this is the overall calculation of the V values mathematically. How we can get mathematically the V values? What is V? It's an orthogonal vector. V values, how to find out V values? Okay. Now you multiply, you pre-multiply A vector with A transpose. You pre-multiply it, A transpose into A transpose into A equal to what is A transpose? What is A actually? A is U into S into V transpose, isn't it? A is actually U into S into V transpose is A. Okay, and raised whole transpose. That means U into S into V transpose whole transpose. That is A transpose into A. What is A? U into S into V transpose. I hope this is clear. Okay, so A transpose, what is A? U into S into V transpose. Here that whole transpose into U into S into V transpose. I hope this is clear. Now, what is US V transpose whole transpose? You know the relation AB whole transpose is equal to B transpose into A transpose, isn't it? This relation you know. AB, the whole transpose, is equal to actually B transpose into A transpose. In the reverse order, you need to apply transpose. So AB whole transpose is equal to B transpose into A transpose. Since you know this relation, it is very easy. A transpose into A, you can write it as here V transpose transpose. What is V transpose? Whole transpose. It is V itself. Okay, so V, S transpose. What is S transpose? S transpose is same as S. Why? Because S is a diagonal matrix. You have only the diagonal elements. All the other elements are zeros, isn't it? So S transpose will be equal to S. Now you can have U transpose. So V S U transpose. Now US V transpose, that is copied here. US V transpose, that is copied here. US V transpose. So once again I repeat, AB whole transpose is equal to B transpose into A transpose. So apply this here. US V transpose whole transpose, that is V transpose transpose, that is V into S. S transpose is same as S, because S is a diagonal matrix, and then U transpose. So V into S into U transpose into US V transpose. Okay. Now here you can have U transpose into U. What is U transpose into U? U into U transpose or U transpose into U is I, because U is an orthogonal matrix. So U transpose into U is I. So here you can write V into S. There are two times. So S square. S into S, S square. U transpose into U, it reduces to I. So no need to write that. Then again V transpose. So V transpose is pending. So V into S square into V transpose. So ultimately you will be getting A transpose into A is equal to V into S square into V transpose. Once again I repeat, V S U transpose into U. U transpose into U is I. So it reduces V into S square into V transpose. So this relation you might be knowing this. Okay, A transpose into A, that means a matrix is equal to V into S square into V transpose. The form is like eigen decomposition. If you are not remembering eigen decomposition, we will go back to eigen decomposition. You are decomposing a matrix. This is eigen decomposition. Please remember that this is eigen decomposition, eigenvalue decomposition you have done in the previous class. Okay, so A equal to V into D into V inverse, or V into V is the eigenvector, D is the eigenvalue. So V into D into then the inverse of V, where V is the eigenvector, D is the diagonal value or diagonal elements which are eigenvalues, isn't it? So V into D into V inverse. So similarly, here also you are getting an equation like this. A transpose into A equal to V into S square into V transpose, or V into S square into V inverse. Okay, just like your eigenvalue V into D into V inverse. Similar fashion, V into S square into V transpose. Actually, V transpose is same as V inverse for an orthogonal matrix. So, V into S square into V inverse. So, by using this eigenvalue decomposition, you can compare that. Okay, so what is V then? V is actually the eigenvector of A transpose into A. Okay, just comparing this relation with the eigen decomposition, you will get that V is the eigenvectors of A transpose into A, and S square, they are the eigenvalues matrix of A transpose into A. Once again, I repeat, the A transpose into A is a matrix. And what is V? V is the eigenvectors of A transpose into A. And S square is the eigenvalues of A transpose into A. I hope this is clear. Just by comparing this relation with your eigenvalue decomposition. Okay, this will give you the eigenvector and S square will be the eigenvalues of A transpose into A. Okay, now this is S square actually. Okay, now you take the square root. Suppose you want to find S, isn't it? Okay, so you want to find S. How to find S? This is S square. You got this S square. So how to find out S? S is actually take the root of this S square, isn't it? So the square root of the diagonal values of S square, they are called singular values of A matrix. Once again, I repeat, this S square means it is the eigenvalues of A transpose into A. Okay, now you find the square root. Now you find the square root of this matrix, you will get the singular values of A matrix. You will get the singular values. These singular values are very important in the case of SVD. These singular values are very important in the case of SVD, singular value decomposition. Okay, so how to find the V value? Actually, V is the eigenvectors of A transpose into A. How to find the V value? V is actually the eigenvector of A transpose into A. And what is S square? S square are the eigenvalues. So the square root of this eigenvalue will be giving your singular values of the matrix A. I hope this is clear. Now, how to get the U values? In order to get the U values, you do a similar procedure. Okay, here you have to find the V values, you have done A transpose into A. In order to find the U values, you do A into A transpose, A into A transpose. Okay, okay. You are post multiplying A with A transpose. So you will be getting A into A transpose is equal to, when you do the similar fashion, U into S square into U transpose. Just like this. V into S square into V transpose, you will get like this. U into S square into U transpose. So what is U? U is the eigenvectors of A into A transpose. What is V? V is the eigenvectors of A transpose into A. And what is U? U is are the eigenvectors of A into A transpose. I hope this is clear. Okay. So this is how you are mathematically finding V value, U value, and S value. So ultimately you can decompose this A matrix as U into S into V transpose. Okay. You can find U, you can find V, you can find S. Okay. I hope this is clear. So I will go to the significance of SVD, or why we are using this SVD, after explaining some programs related to SVD. So we will continue in the next video clip. Thank you.